All right, buckle up, everyone, because today we are diving deep into some cutting-edge machine learning research.
Oh, yeah. Sounds intense.
It is, it is. We're talking about a paper that tries to make AI more transparent.
Because right now, it's often a total black box, right?
Exactly. You put data in, you get results out, but understanding why the AI made those choices, well, good luck with that.
This paper wants to crack open that box.
It really does. And it focuses on something called recurrent neural networks, or RNNs for short.
RNNs, they're everywhere, aren't they? Language translation, you name it.
Oh, yeah. Financial forecasting, even analyzing your heartbeat.
But as you said, they don't show their work, those traditional RNNs.
No, they don't. So this paper is all about almost-linear RNNs, or AL-RNNs.
They're the heroes of our story.
You got it. Accuracy and interpretability, that's the goal.
Sounds ambitious.
It is. But before we get to the AL-RNNs, we need to talk about something called dynamical systems.
Okay, dynamical systems, so what are those?
Basically anything that changes over time.
Yeah. Give me an example.
Okay. Weather patterns, how about that? The stock market. Even the neurons in your brain.
Ah, got it. So things that are constantly in flux.
Right. And, the traditional ways of modeling those systems, they can get really complex.
You said it. Complex is an understatement sometimes.
Totally. So researchers have been using something called piecewise linear, or PWL systems, to simplify things.
Okay, so piecewise linear. Break that down for me.
Think of it like taking a really complicated curve and breaking it down into smaller straight lines.
Like connect the dots.
Yeah, exactly like that.
Okay, I can see how that would simplify things.
It does. It's like instead of looking at every single peak and valley on a mountain range, you just see those major contours, those elevations.
You get the big picture without getting lost in the details.
Exactly.
Makes sense.
So we have these complex systems, and then we simplify them with PWL models. But where do the RNNs come in?
Well, creating those PWL models by hand, it can be a real pain, especially when you're dealing with tons of real-world data.
I bet.
It is. That's where RNNs, those neural networks, come in. They can learn the dynamics of a system from the data itself.
So they're like those super smart apprentices that can figure things out without needing step-by-step instructions.
Yeah, precisely. They learn by doing, by observing.
That's incredible. So RNNs could be our shortcut to creating these simplified PWL models, right?
You got it. But those regular RNNs, there's still those black boxes we were talking about, remember?
Ah, right. They learn the dynamics, but they're not telling us how they're doing it.
Exactly.
Okay, so let's bring back the AL-RNNs, our heroes.
Yeah.
What's their secret sauce? How do they make things more transparent?
So their magic lies in their structure, their architecture.
I'm intrigued. Tell me more.
Okay, so unlike regular RNNs, they combine these linear units with a few special nonlinear units, these things called ReLUs.
ReLUs, got it.
And this allows them to learn those PWL representations, but with a surprisingly small number of pieces.
Jesus, okay, you're going to have to explain that.
Yeah, of course. Remember those straight lines from our connect the dots analogy? Those are the pieces?
Okay, so fewer lines, simpler picture.
Exactly. And simpler means easier to understand.
Got it, got it. So it's like they're finding those key turning points in the data, right?
Yes, highlighting those moments where the system shifts gears, those aha moments.
Okay, so now I'm seeing the light. But how do we actually read this simpler picture? How do we go from those pieces to understanding what's happening?
So this is where things get really cool already.
Hit me with it.
So AL-RNNs, they naturally create a symbolic code out of their dynamics.
Symbolic code, like a secret language.
Kind of. Think of it like this. Each piece, each straight line gets assigned a letter.
A letter? Really?
Yes. And as the network processes data, it moves from one piece to another.
So it's creating a sequence of letters.
Exactly. It's like it's writing a story about how the system is evolving over time.
Hold on, we're translating the language of the RNN into letters. It's mind-blowing.
It is pretty cool. And you know what's even cooler? The paper actually provides mathematical proofs that show this symbolic code isn't just random. It actually keeps all the important properties of the original system.
Proofs. Math. All right, I'm listening. But for our listeners who might not be, let's simplify it. What's the key takeaway here?
The takeaway is that this symbolic code, the sequence of letters, is a really accurate representation of the original system.
Okay, I'm with you so far. So if the original system has a stable state, like a ball at the bottom of a bowl, its symbolic representation will also have a point representing that stability.
Yes.
That's pretty neat. Okay, I'm on board with the theory, but Did they actually put these AL-RNNs to the test?
Of course they did. They ran experiments, lots of them, on benchmark systems, systems with known behaviors.
Okay, like a testing ground.
Right. And they also used real-world data, stuff like EKG and fMRI recordings.
Wow, so they really threw everything at it.
They did, and guess what?
Tell me they passed with flying colors.
They did. They aced the test. Not only did they accurately reconstruct the dynamics of those systems, but they also gave us those beautifully interpretable models.
So they could predict and explain.
Yes. And in those benchmark systems, they even rediscovered those simplest PWL representations just from the data.
No way. So they were able to find the most elegant way to represent these complex systems without any prior knowledge.
Exactly.
That's amazing.
It is. And that ability is incredibly valuable, because it gives us a much clearer view of how the system is actually working.
Okay, I'm sold on AL-RNNs. So let's get to those EKG and fMRI experiments. What did they discover when they applied this to real-world data?
All right, so with the EKG data, the AL-RNNs gave them a really clear breakdown of the heart's electrical activity over time.
Like seeing a heartbeat in slow motion.
Kind of. It's more like seeing the heartbeat broken down into these distinct phases because they're working with those PWL representations.
Okay, so like a conductor score, highlighting all the important parts of the music.
Perfect analogy. And what's fascinating is that those phases, they often lined up perfectly with specific events in the heartbeat.
So we're not just getting a pretty picture, we're getting a picture that actually tells a story about how the heart works.
Exactly. And they even pinpointed when the Q wave, that's a crucial electrical signal, was activated.
Wow. This could be a total game changer for understanding and treating heart conditions, right?
Absolutely. Now, the fMRI experiment, that was super interesting, too.
Brain decoding time. I've been waiting for this.
I know, right? So they used the AL-RNNs to analyze brain activity while people were doing different tasks.
Tasks like what?
Oh, different cognitive tasks, memory tasks, visual tasks, that sort of thing.
Got it. So what did they find? Spill the beans.
Well, remember how those PWL pieces correspond to different phases of a system's behavior?
Yeah, those straight lines.
Right. Well, they found that those pieces often align perfectly with the stages of the tasks people were doing.
Hold on. Are you saying that these AL-RNNs were picking up on different thought processes?
That's exactly what it looks like. As the person switched between tasks, the AL-RNN switched between those pieces too, suggesting it was learning to represent those different cognitive processes.
That's wild. So it's like the network is learning to read minds.
It's a very compelling result, and it really highlights the potential of AL-RNNs to help us understand how the brain adapts to different mental challenges.
Okay, before we start worrying about AI reading our thoughts, let's talk accuracy. How reliable were these results?
Well, they actually achieved really impressive results in the fMRI data.
Like how impressive? Give me numbers.
Even with a limited number of pieces, they could accurately reconstruct the brain's complex activity patterns.
Wow. So even with a simplified model, it was still able to capture all the nuances of the brain.
Pretty much. It's really remarkable how well it performed.
All right, we've covered a lot of ground here, but there's still so much more to unpack, right?
Oh, yeah. We haven't even touched on the connections to symbolic dynamics and all the other cool stuff.
Symbolic dynamics. That sounds intense.
It is. But we'll save that for next time. Stay tuned, folks. It's amazing how these AL-RNNs bridge the gap between these continuous systems that change over time and the world of symbols like codes or letters, right?
Yeah, it is. I love that we're finding ways to simplify these complex ideas. But I have to admit, symbolic dynamics, that sounds a little intimidating.
Yeah, it can sound that way, but it's not as complicated as it sounds.
Okay, good. So break it down for me. What is symbolic dynamics?
Well, imagine a pendulum swinging back and forth, right?
Okay, got it. Classic pendulum.
Right. Instead of trying to track its exact position at every single moment, we divide its path into zones and give each zone a symbol.
So instead of smooth swinging, we're looking at it in chunks.
Yeah, exactly. Like a simplified animation. You got it.
Okay, so as the pendulum moves from one zone to another, it creates a sequence of symbols, kind of like a code, right?
Exactly. And this code captures the essence of the pendulum's motion, but in a simpler way.
It's like turning a smooth melody into individual notes.
Right.
We might lose some of the finer details, but we get the basic structure of the music.
Perfect analogy. And the amazing thing is, even with the simplification, we can still learn a lot about how the system behaves.
Like what kind of things can we learn?
Well, we can spot those repeating patterns, see those bursts of chaos, and even try to predict how the system might evolve over time.
So it's like we're finding hidden messages in these symbol sequences, cracking the code of this system, right?
You got it. And the connection between AL-RNNs and symbolic dynamics, it's really exciting because it opens up new ways to understand how AI learns and makes decisions.
Because if we can look at those symbol sequences from the AI, we can understand why it makes certain choices.
Precisely. It's like we're giving the AI a way to explain itself.
That's amazing. Okay, so how do we actually extract these symbol sequences from the AL-RNN? It's not like it just spits out a string of letters, right?
No, but it's pretty intuitive, actually. Remember those pieces of the PWL representation?
The straight lines.
Yes. Each one gets assigned its own unique symbol.
Okay, okay.
And as the network processes data, it jumps from one piece to another.
Creating that sequence.
Exactly. It's like watching a dot move on a map, and each jump represents a different symbol.
Oh, I like that. Okay, you also mentioned earlier these mathematical proofs that show these symbol sequences aren't just random, that they keep important properties of the original system. Can you give us some examples of that?
Sure. Let's start with those fixed points, those places where a system stays the same over time, like a ball at the bottom of a bowl.
Got it.
One of the proofs in the paper shows that if the original system has a fixed point, its symbolic representation will have one too.
So we don't lose those important landmarks when we simplify things.
Exactly. And another proof, it deals with those cycles, where a system repeats itself over time, like a planet orbiting a star.
Okay, yeah.
This proof shows that if the original system has a cycle, its symbolic representation will have a corresponding cycle, of the same length even.
So it keeps the rhythm going.
Exactly. Now, not all systems are so predictable, right? What about chaotic systems, where tiny changes can lead to wildly different outcomes?
Yeah, those are the ones that keep me up at night.
Well, the good news is those chaotic systems, those can be captured by the symbolic code too.
Really?
Yeah, there's a proof in the paper about those trajectories that never repeat, those chaotic paths. And it shows that if the original system has one of those trajectories, its symbolic representation will have a corresponding one as well.
So even in the midst of all that chaos, the symbolic code can still represent those unpredictable behaviors.
Exactly. We can find order even in randomness.
This is incredible.
Yeah.
We've gone from abstract math to like unlocking the secrets of the universe or something.
I know, it's pretty amazing. And this is just the beginning. This paper focuses on AL-RNNs, but I think these ideas, they could really change how we think about machine learning in general.
You think so?
Yeah, I really do. By connecting the continuous and the symbolic, we can make AI more transparent, more understandable.
So we can move away from those black boxes and actually see what's going on inside.
Exactly. Okay, so let's get back to the paper for a second. Did they actually test out the symbolic coding stuff in those real-world experiments, with the EKG and fMRI data?
Yeah, that's what I was wondering too. Did they actually look at the sequences?
Oh, they did. They definitely did. They went beyond just reconstructing those dynamics and really dug into those symbolic sequences that the AL-RNNs generated.
Okay, so what did they find out about the heart and the brain? Give us the juicy details.
Well, with the EKG data, remember how we talked about those pieces of the AL-RNN aligning with specific heart events?
Yeah.
Well, analyzing those symbolic sequences, it just confirmed that alignment. It gave them even more insights into the heart's electrical activity.
So the sequence is like a detailed narrative of what's happening in the heart.
Exactly. We can see those key events in the electrical cycle, see how it all unfolds.
It's like reading the heart's diary or something.
I love that. And this gives us a way to analyze heartbeats that traditional methods just can't do,
Like what kind of things?
We can spot those tiny variations in the timing of events, which might be signs of underlying conditions.
Oh, wow. So it's like a superpowered EKG.
Yeah, exactly. It's showing us those hidden details that we might otherwise miss.
Okay, that's amazing. What about the fMRI data? What did those symbol sequences tell them about the brain?
So they actually used those sequences to measure how well the network was distinguishing between those different task stages.
So they weren't just guessing, they were actually quantifying how good the network was at recognizing different thought processes.
Right. They calculated the probability of the network switching between different symbols based on what task the person was doing.
So like a map of the brain's mental landscape, showing how it jumps from one thought to another.
Exactly. And it was really remarkable how accurately it could capture those transitions.
It's like watching a thought unfold, seeing those different mental states in action.
It is. These AL-RNNs are really something else, aren't they? They're not just imitating intelligence, they're giving us a glimpse into what makes us intelligent.
Yeah, I'm blown away. But before we get too carried away, I want to circle back to something we were talking about earlier. Finding the right number of pieces for those PWL representations.
Ah, yes, finding that sweet spot.
Right. We discussed observing the performance, using those regularization techniques. But are there any other tricks to find that balance between accuracy and interpretability?
So researchers are definitely working on that.
Okay, good. What kind of things are they looking at?
Well, one really promising area is using information theory.
Information theory. Okay, remind me what that is again.
So it's a way to measure the complexity of those symbol sequences.
Got it. So the idea is that as we add more pieces, the complexity of the code increases, but at some point, it doesn't add any new information.
Exactly. It's like finding the point where the code becomes redundant.
So we want to find that sweet spot where we have enough complexity to capture the important details, but not so much that it becomes overwhelming.
Precisely.
That makes sense. But are there any downsides to using these AL-RNNs? Are there situations where they might not be the best choice?
Well, like any tool, they have their limitations.
Like what?
Well, one thing is they need a lot of data to learn those PWL representations effectively.
Okay, so data-hungry models.
Yeah. If we don't have enough data, other methods might be a better choice.
Makes sense. Makes sense. What else?
Another potential issue is that the interpretability of AL-RNNs, it depends on us understanding what those symbols actually mean.
So we need to be able to crack the code.
Exactly. If we're dealing with a system we don't understand well, even a clear symbolic representation might not be helpful.
It's like having a book written in a language we can't read.
Yeah, exactly. In those cases, we might need to combine AL-RNNs with other techniques, maybe even get some help from experts in that specific domain.
So it's not a magic bullet, but it's a powerful tool for understanding complex systems, right?
Absolutely. And I think it's a really important step towards making AI more transparent and trustworthy.
My mind is still buzzing from all this talk about symbolic dynamics and AI uncovering these hidden patterns in complex systems. It's amazing. But before we wrap things up completely, I want to go back to those experiments with the benchmark systems, the Lorenz and Rössler systems. I know we touched on this earlier, but you mentioned that the AL-RNNs were able to rediscover the simplest PWL representations for those systems just from the data. Can you explain why that's so significant?
Oh, absolutely. The Lorenz and Rössler systems, they're classic examples of chaotic systems, where even tiny changes can lead to completely different outcomes.
Yeah, the butterfly effect and all that.
Exactly. They've been studied for decades, and mathematicians have figured out these really detailed PWL representations that capture their behavior.
So those PWL representations, they're like the instruction manuals for these chaotic systems.
Exactly. Simplified blueprints that break down those complex behaviors into those straight lines, remember?
You're right.
So what's amazing is that the AL-RNNs, they were able to learn those exact same minimal representations just from the data without any prior knowledge.
So they were able to figure out the most elegant way to describe these systems just by observing them. That's incredible.
It is. It shows how powerful these networks are at extracting the essential information from a system, finding those core features that really drive everything.
Okay, I'm impressed. But why is finding those minimal representations so important?
Well, think about it. The simpler the representation, the easier it is to understand, right?
Makes sense.
So this means we can use AL-RNNs not just to model those systems, but to really understand how they work.
So it's not just about predicting the future, it's about understanding why things happen the way they do.
Exactly. And that's where AL-RNNs really shine. They bridge that gap between those black box AI models and something we can actually understand.
Okay, I'm with you. Now, what about those real-world data sets, the EKG and fMRI data? Did they analyze those systems in terms of those minimal representations too?
They did, and this is where it gets even more interesting. So for the EKG data, they found that the stable points, those places where the heart's electrical activity settles down, they tended to cluster in a specific region.
Hold on, I'm having trouble visualizing this. Can you paint me a picture?
Sure. Imagine each point in space represents a different pattern of electrical activity in the heart.
Okay, got it.
They found that the points where the heart stabilizes, they fall within a particular slice of this multi-dimensional space.
So like a preferred zone of stability in the heart's electral world.
Exactly. And what's even more interesting is that this zone, it aligned with something called the first principal component of the data.
The first principal component. Okay, remind me what that is again.
So principal component analysis, it finds those main axes along which data varies the most. So the fact that those stable points aligned with the first principal component, it means the heart tends to stabilize along that direction of greatest change.
Wow, that's fascinating. It's like the heart is trying to find a balance between staying steady and being adaptable.
I like that. And they found a similar pattern with the fMRI data too. Those stable brain activity patterns, they often aligned with the first principal component as well.
So this idea of stable states aligning with that direction of greatest change, it seems like a recurring theme in these biological systems.
It's a really intriguing observation, and it points to the potential of AL-RNNs to uncover those universal principles, those rules that govern how complex systems work, no matter what kind of system we're looking at.
This is mind-blowing stuff. We've gone from abstract math to understanding the heart and the brain, and it feels like we're just scratching the surface. What are some of the exciting directions for future research with AL-RNNs?
Well, one area I'm really excited about is finding even better ways to create those symbolic codes. Right now, we're assigning one symbol to each piece of the PWL representation.
Right, those straight lines.
Right. But imagine adding more detail to those symbols. Instead of just saying the system is in state A, we could say the system is in state A and doing this, or the system is in state A and about to do that.
Ah, so we can pack even more information into those codes.
Exactly. And that would give us an even richer understanding of the system's behavior. Another exciting direction is applying AL-RNNs to other real-world problems like climate modeling or financial forecasting.
Oh, yeah. Imagine decoding those hidden patterns in the stock market or understanding how climate change is going to unfold.
Right. I think AL-RNNs have the potential to revolutionize how we approach these complex challenges.
Well, I'm definitely convinced this has been an incredible deep dive, and I can't wait to see what the future holds for AL-RNNs and our understanding of complex systems. Thanks for joining us on this journey, everyone. Until next time, keep exploring, keep questioning, and keep diving deep.